So today we are going to start with building our first neural network. So today essentially what we are going to do is, till the last class, you have got a bit of introduction into what are the basic challenges with machine learning, where does machine learning fit into as a problem, and what do you need to have an idea about the data, about the model, and other factors around it as well. Now today what we are going to do is, we start with some of those aspects. We will not cover all of them today, we will eventually through the course cover. But today I am going to essentially get you introduced to building your first very simple neural network, which is a very lightweight model as we call it. So we will understand from a very problem perspective. So I have a problem at hand and I will start from there to understand exactly how do you come to the analysis of a data, because from data to statistics is what we have done, but then we need to understand what exactly is that data. That is the first part. Now given that we know about the data, can we derive something about the model from that data itself? So these are the facts which we will start with today. Now, pointer. So, say about our starting point is essentially the biological neuron. Okay. Now, all of our brains and everything, whatever we have studied in biology, you know that they are made out of neurons. Okay. Now there is this wonderful talk which I would refer to you. This is by James D. Caldo from CVPR 2017. It's a keynote which he had given down over there. And whenever you have time, please watch this one. It's about a 45 minutes keynote which he had. But this is a wonderful connection. So James is a neuroscientist. So essentially he is somebody who studies about biological neurons, but he does a lot of electrical engineering experiments on top of it. So essentially he senses when there are multiple neurons which are conducting and sending some signals across to each other, he has small electrodes which are placed at those junctions as well as on the neurons itself to understand like how fast they are communicating, what is the magnitude in which they are communicating. There are some interesting facts which I got to learn from this particular session which I was attending. So one thing was that we express things in terms of intensity. So for us, large is a large number. So when you have a image or something over there, so if some spot is bright, then that spot is denoted by a very high number value. If some spot is dark, then it's denoted by a near zero value over there. But then for us, within our body, whatever neurons are there, they don't exactly communicate in that way. So in fact, in our body, the neurons communicate in a very different way. And that's a more logical way. So what happens as a result of that is that it does not lose out any critical information. So it essentially communicates using some sort of spikes. Okay. Now the frequency at which these spikes origin, that's what is controlling the intensity. So if the frequency of the spikes over here is very high, then that indicates a very high intensity. If the frequency of the spikes is very low, then it indicates a very low intensity, and no spiking means no action, nothing going down over there. Now, and you can pretty much relate. So at the end of this talk, he draws these parallels between some of these very well-known neural networks. So one of them is a LeNet. You might have heard about it, and we will be studying about what a LeNet is. Today we are going to start with a much smaller version of that one itself. Now, he has proven that within our brains, the way we recognize objects, at least for numbers and alphabets, the circuit within our brain has a one-on-one parallel to exactly what a LeNet in terms of our neural networks in deep learning mean. And that's where we are today, and it's really interesting. So please have a look at that one. Now to bring down to what I was speaking, essentially, if you look over here for any biological neuron, you would have basically these things which are called as dendrites and these points which are called as synapses. Now what these dendrites do is they essentially communicate from one neuron to another neuron, and the synapse is the point where one neuron connects with another neuron. So a neuron can connect with multiple neurons can also connect with a neuron, and that all of that will happen at the synapse over there. Okay. You have an axon which is essentially that body or the fiber along which it is communicated. So for a fixed length of physical space, it will be connecting and it will be going down around over there. Okay. Now here, if you carefully look at it, what happens around these synapses, the synapse is something which guides what is the amount of intensity of a signal which is getting propagated from one to the other. Okay. Now, critically, how many of you have some idea about filters? Low pass filters, high pass filters? I mean, majority of you have some idea. of low pass filters, high pass filters. So now if I have spikes, spikes are essentially what they are basically impulses and a train of impulses at a certain frequency which it is going. So now if this one, this synapse over here has some sort of a filter, say a low pass filter, then all spikes which are of a frequency lower than that pass frequency will go through it, others will not go. Say if it has a high pass filter, then others will go. Okay. So that's essentially how it modifies what amount of intensity it has to send from one neuron to the other, and that's how decisions are made. Now along with that, what it also introduces is a form of non-linearity. See, whatever is the rate of arrival of the spikes over here is not the rate of transmission of the spikes over here after the synapse, right? Because you have a filter over there. Now as a result of it, if my spikes are coming at what particular frequency, then all frequencies are not going down after the synapse to the other part of it. That will be another important part which will go. Now we need to have a similar kind of a model in our mathematical neurons as well. The only difference is that we try to draw some sort of parallels over here and make some changes. Okay. So let's get into a basic system, and from there I will get into what is that change we do in the neural network. Now say I give you this whole problem of recognizing handwritten digits. Okay. Now as humans we are able to recognize. Is everybody able to read what are the digits written over here? You are able to read it? Okay. So now if I ask you that let's build a computer vision system. So it will have a camera, it will have the output of the camera will go to some computer over there, and that computer is going to run a piece of code which is going to tell me exactly what is the digit in terms of either its binary value, its octal value, hexadecimal value or ASCII value whatsoever. So it's going to give me something which is a computer readable format. That's my point over here. Okay. So let's look into how we are going to do it. One is, if I look at this whole picture, this whole palette or canvas, whatever you call it, then there are a lot of digits over there. Now I cannot obviously recognize all the digits together in the simplistic case. In a simplistic case, what I need to have is I will move my camera such that it is looking at only one digit at a time in some way. So I can have a mechanical way of moving it out. Somewhere later on in the class we will also learn about that you can give this whole canvas itself, and it can, there will be some neural networks which will help you isolate exactly 1111 separate digit over there, and then you will analyze what this digit means. So you know that there is a number written, that is what that neural network will do, and then ask the next neural network to tell, okay, there is a number, you recognize what is the number. But let's solve the later part of it, which is let's recognize a number. Given that I give you a small patch over there, a part of this whole image, or maybe the camera is looking very close enough to that one and it's getting only a small part of this whole canvas available to it, and then it's going to make an inference of it. Okay. Then what is it going to do? Let's look at this small point over here. There is some number within this patch which is there. Okay. We as humans are able to tell that this is the number 5. Okay. To a certain extent I might also tell this is the number 8 where some part of the ink got chipped off. This is also the number 6 where this part of the ink got chipped off. There can be a lot of things which you can say. In fact, there will be a lot of confusions which you would see somewhere later on as well. Like this number becomes really complicated, whether this is 9 or this is 4 or this is 1. So in the rows of 9 in the middle, somewhere over here, something which looks like 9, 4, 1, somebody can also tell that that is 7. So there can be a lot of these confusions as well which would keep on coming. So now I will have a camera. This camera is going to give me something which is called as a digital image. Now what this digital image is, whatever the camera acquires, that is essentially an intensity at a particular point. Okay. So how many of you have idea about cameras? Cameras? A pinhole camera everybody knows, you have studied in his school. Pinhole camera everybody is aware of it. Okay, great. Now for an electronic camera, which is there in your smartphones or a webcam, how does that work? Any idea for that? Overall, I'm not asking you basically what is the rolling of bandwidth of the sensor and other things. That's not what is there within our reach. So you essentially have a small lens, right, for any practical camera. From there it's going to cast an image on some image plane, and what you will have over there is basically an electronic sensor. And what this sensor does is, whatever is the intensity of the photons coming over there, it's going to report that as a electronic value, and that value will go through something called as an A to D converter, an analog to digital converter, and then you have a digital reading corresponding to that. So we get down something like this over here. So 0 would mean that the whole pixel is dark, black, and 1 would mean that the intensity over there is white. Okay. So this is a part of it because I mean, it's a large size canvas. I have just replicated only parts of the rows and columns of this one. So it's essentially going to be some zeros and ones. So wherever it corresponds to white, that is going to be 1. Wherever it corresponds to black, it is going to be 0. That's essentially, and any shade between perfect black and perfect white is a number between 0 and 1. This is our assumption over here. Okay. Now what more can you say about this one? One is that it is in the range of 0 to 1. Okay. So if it is in the range of 0 to 1, then I need to have something which is called as a precision of the number system. So I will need to have a particular precision of number system. So if either it's floating point or it's fixed point, but it cannot be integer, because if it is an integer, then numbers between 0 and 1 cannot be represented. Okay. So now if I have a floating point or a fixed point, then there will be fixed number of bits which will be used in order to encode this one. So I can have a 16-bit system or 32-bit system or 64-bit system or even 128-bit system, which is not a very regular way to have it. In general, we have over here say something like a 32-bit system, which is called as a float 32, a floating point 32-bit number system to do that one. Now you take this one, this whole patch over here, this whole matrix should also have a fixed size in terms of its x and y dimensions. That should also be there, and that will be proportional to whatever is the output from the camel, and that will not keep on changing, because you see when you click a picture from your smartphone, the size of that picture is always the same, which means the number of rows and number of columns, that is never going to change in any way. Okay. Now let that whole thing be called as x, or a sample for us. Okay. A sample is not a pixel, but a sample is that whole set of all the pixels which constitutes an image, and that is my x. So now if we go back to whatever we had done in the last week, so I had all the sufficiency criteria which you will have to look into and explore on the samples itself. So we will need to satisfy that in terms of x, where this whole thing is what is called as the sample. Now that sample goes into a neural network over here in that blue trapezium. Okay. And it's going to give me an output, and this output is essentially omega hat, or what is the predicted class in that sample. Okay. Now this is very simple. What it does essentially is that it calculates what is the posterior probability over all the classes for a given x. So given that this input goes into the neural network, it's going to find out first what is the posterior probability for all the classes, and then whichever class has the highest posterior probability, it's going to do that. So now that would make it very clear that this neural network is solving nothing other than just a Bayes rule. That's what this neural network is going to do over here. So it's a very elegant way of telling that this is doing all of this, but at the end of the day, it's going to solve just the Bayes rule and nothing beyond. Okay. Now we need to now borrow down all of our learnings which we had done in terms of Bayes rule in order to see whether this is a satisfiable problem or not. So whether this is solvable in any sense. Okay. Now from there, let's get into the point. The first is you will look into the data space of this problem. That's how we have started. We had the data space of the problem, we had the model space of the problem, and then we had the first one was the data, then was the model, and then was the control plane of the problem, where we were solving the optimization so that it fits with the minimum error over there. So today we are going to look into this data plane and the model plane. Okay. Tomorrow we will come into, not tomorrow, a bit later on, I think 2 days later we will come into the optimization plane of the problem. Okay. Now in the data plane of this problem, so what inference can you draw from this? So say this is your training data set which is given to you. So can you comment something about the training data set itself? So what was the first thing we were investigating? First is you had to find out what was the number of classes. Okay. So what is the number of classes over here? 10 classes. Okay. So essentially this is the first thing which you know about this one, that there are 10 classes over there, and we can name them something like omega 0 to omega 9, such that omega 0 corresponds to the digit 0, omega 1 corresponds to the digit 1, and similarly omega 9 corresponds to the digit 9. Okay. Now this index over here in the subscript, that does not carry any sense with whatever is the class. So in fact you can also start with a nomenclature saying that omega 9 is 0, the digit 0, omega 8 is the digit 1, or any order, but you need to remember it. I mean, your system needs to be very pre-specified, like which one maps to exactly which digit, otherwise that will create a confusion. And that confusion will be in the control plane, not in the data plane or the model plane in any way. Next, I also see that there are 20 samples per class. So what you can do is every row is essentially one class, one digit, and you can count. So there are 1, 2, 3, 4, 5, 6 like this, 20 such columns over here. So essentially there are 20 samples per class which I have. This is the first thing which I know. Okay. Now can somebody comment on the entropy of this class distribution over here? Entropy over class distribution. Are we reaching log 20? Maximum entropy will be log of 20. So are we, not log of 20, log of 10. Are we reaching log of 10? Is this equiprobable? This is equiprobable. Yes, because there are essentially 20 number of samples per class and there are 200 samples in total. So for any sample to occur is basically 20 by 200, which is essentially 1 by 10, and that is the maximum probability at which it should come down. So essentially this is a very good distributed one where the data set has the maximum entropy which can be there for this particular problem. So one part is satisfied. See, these are things which you will have to do. You will have to look into that entropy part and gauge whether my data set is skewed or not skewed. So this is an equiprobable data set, and how we came to that one was a very simple way, because there are lots of classes. How many will you compare? If you want to compare probabilities, you will compare one pair at a time. Can you comment on the whole thing together? The best way is just calculate out the entropy, because you know what can be the maximum entropy for a given number of classes. If it matches that maximum entropy, then yes, this is a very good problem, that you have equiprobable distributions and equal number of data coming down over there. Now let's get into the next part of it. Next is, we look into one of these images and then you have this array present over here. Okay. So when you are coding it in Python, you will get something like a NumPy array in general. Okay. Now that you have this array, can I comment something on this array as well? So one is, I can look into what is the total number of rows and columns, right? So over here, we would get this as 28 and 28. Okay. That 28 as a number has a very interesting connotation, why it's 28, and I think on the Thursday class we are going to do that lab. We'll run this experiment. All of you will be trying it out on your laptops itself, and you will get down this 28. So remember this 28 as a number itself. We'll do this experiment on Thursday. Okay. So what this would mean is that there are 28 columns and there are 28 rows over here, and the values can be anything between zeros and ones, and this is a FP32. Good. Now that we have this, the next question comes down is this a 2D array or a 3D array? 2D array. Okay. So essentially, how many such numbers are present in this one whole array? 28 into 28, 28 square, which is 784. Okay. I can remember that at the top of my mind because this data set and the size is very constant. This is a very standard size of 28 cross 28, so we just remember it. Okay. Next, you will get down a bigger data set, which is where the sizes are 32 cross 32. There it will be 1024. And after that, you are going to get it as 224 cross 224. After that, it will come as 256 cross 256. And in general, these are resolutions, and more than, you can go even beyond that. So some of the data sets are 1024, 1024 as well. There is a particular one which is called as celeb data set, celeb A. So it's celebrity faces of very high resolutions, and every image is 1024 cross 1024 RGB pixel image over there. Now here, from all of this, the next part, whatever we could get on the data, we have got it. The next part is to build our model. And that's where all the interesting stuff now starts coming in over there. First is, I have this image where I know that there are 28 columns and 28 rows. So what I will do is, I will start ordering them in some sort of a column measure rearrangement style. So either it can be a column measure or this can be a row measure, any one of them, but whatever you choose, you need to stick to them. It cannot be that for the first sample I do a column measure, for the second I do a row measure, then for the third I do a row measure, fourth I do a column measure, and then, so that cannot keep on randomizing itself. You need to keep it constant. So if I am doing a column measure orientation, let's column measure. If I am doing a row measure, then let it be row measure. Okay. So imagine this, on your RAM, whenever there is a 2D or ND array which is stored, either it's a row measure or a column measure, any one of them. And it does not keep on changing, because if it keeps on changing, you give a 2D array of say 10 cross 40 and you get a, when you are reading, because you don't know exactly what it was, you would have read a 40 cross 10. Now that doesn't happen, and that's because you follow one of these conventions. So if we do that, essentially we are going to stack all the columns one after the other. Okay, so first column will have 28, next will have 28, the third column will have 28, like this it goes, and last column also has 28, it comes down over here. Okay. Now essentially that would get me 784 such elements which are located over here, so it becomes a 1D array of 784 elements. Now this whole array goes into this neural network over here, and that produces an output, and this output is going to be a 10 element array. Now can somebody tell me why do you think this is going to be a 10 element array? Because you have 10 classes. So each element over there is going to give you a value in the range of 0 to 1, which essentially is supposed to be that probability of getting a particular class given that you have an X. And since you have 10 classes, so you are going to have 10 over here. Okay. Now if we change this problem and tell that instead of getting handwritten digits, you have handwritten digits, you have handwritten alphabets in lowercase, and you have handwritten English alphabets in uppercase as well. And this is for the English alphanumeric system. So in that case, how many neurons will you have in the output? 62. So essentially there are 26 alphabets in lowercase, there are 26 alphabets in uppercase, makes it 52, and you have 10 digits over there which will make it 62. So this is how you can change on your output side. So there are some constants on the input which you know, and there are some constants on the output which you know from a problem definition, right? Now look at it. If you are training a model in order to recognize all digits, that will have 10 outputs. Now if you want to use it in order to recognize alphanumerics, it cannot directly be ported over there. You have to make a change because this output 10 cannot be directly mapped onto 62. So there has to be a change in the model itself, in the architecture, right? So it's not just a training problem which will come over there associated with it, but you will also have a model adaptation problem which will come in. So when we, in the later on class, when we get into domain adaptations, as one of the measures by which we can rapidly train our existing algorithms to work on some improvised versions of problems, then we will also have to relook whether we need to really change the model as well or not. So there are some parts which are called as domain restored adaptations, and there are somewhere where you have a domain modified, a model modified domain adaptation and a model restored domain adaptation itself. So those will be facts which will come over there eventually. Now let's get into what this neural network will be composed of. And this is where I will again draw that parallel to a biological neuron which I spoke at the start of the class. Okay. So essentially, say I have this set of inputs over here and there are some d number of inputs. For our this digit recognition case, what is the total number of inputs which will go? 784. You have 784 numbers which together represents one sample in a vector which is x in bold, lowercase italics. Okay. Now each of them will have a scalar value which is from x1, x2 up to x784. For me this is xd, some generalized notation. Okay. What I can do is, we can all weigh all of these inputs with some weights, say w1, w2 up to wd, and then we take all of this and sum it up. Along with summing it up, we also add a DC shift to this one which is called as a bias. Now that is also denoted by this notation which is called as w0. Okay. So what will happen over here? What will happen over here? One is that you have different components which are not equally weighted but with some different contributions going and adding over here. This is the first thing which you get to see. Next thing is you also see that there is a bias which is getting added over here which will do a DC shift. So essentially that would mean that if all the inputs are 0, still your output is not going to be 0. Your output may be non-zero. That is what it will ensure. Okay. Now for a biological neuron, how do you come from a biological neuron to this one? So essentially you had a lot of those dendrites over there, and lot of synapses around dendrites. Okay. These synapses were what was implementing this particular one. So if you have multiple connections over there and through the synapse that filter, that is going to have this W1, W2, all of these different kind of weights. So which one am I going to do with what amount of intensity? Okay. Next from here, so till here, so from a systems theory, can somebody tell me whether this is a linear system or is it a non-linear system? Linear system, are you sure? Yes. So this is a line equation, but this is not a linear system. There is a difference. A set of linear equations does not necessarily mean a system is linear. A linear system has this definition. If y is the output of a system and if I say y is the output given x is the input. So you can write this as y is equal to f of x. Okay. Now if I have ax1 plus bx2 as my input, then my output in that case should have been ay1 plus ay2. But here that is not what will happen, because what would do is this constant over here will get added twice. So if there are multiple number of components I am adding, that will get added twice, and that is where the whole non-linearity comes into it. So though this can be represented, I will later on show that this can be represented as linear algebra, but linear algebra does not mean that always the system is linear. Okay, that's one of the first thing. So a neural network is actually a non-linear system. Okay. So this is the first scale of non-linearity, and this is what is called as the domain non-linearity. Okay. So in the domain of x's, in the value of x's, everything is going to be non-linear. Okay. Next, from here we get an output which is called as a of x, and this a of x enters into something which is called as a non-linear transformation called as g. Let's denote it by g, and this gives you an output which is y. Okay. So here we can write this pretty much as a set of equations, and how these equations can be written down is something like this. So x can be a tall vector, a column vector essentially over that. Okay. And you can have this a of x, which is essentially this bias plus this summation, or that is essentially the multiplication of this weight vector and bias taken as a row vector, and you have x and 1 taken as a column vector. So this becomes a very standard matrix multiplication problem and nothing beyond it. See, that's simple. Now that is where neural networks can be so easily and so fast implemented on most of our computer based systems, because of this one particular aspect over there, that this can be implemented as a matrix multiplication. Now most of our modern systems are very fast in terms of matrix multiplication because they have hardware units in order to do that. So no more, maybe in your PDS class you had done a matrix multiplication by writing this summation with for loops, 2 for loops, 3 for loops, based on whatever is your dimension of the matrix over there. But in our current systems we don't do that anymore. In our current systems you can pretty much give 2 arrays of fixed size, maybe 32 elements, 64 elements, whatever is the hardware limitation over there, and it can give you an output, a scalar output of that matrix multiplication itself, and that's what saves a lot of our time over here. Okay. So as a result of that, today when we represent any of these neural networks like architectures, we very heavily make use of a matrix notation of representation, and in fact that's what we will continue throughout the class itself. From there you get down this a, which goes through another function which is called as g. So we will come into what is that g, which is called as activation function. There are different ways in how activation functions can exist, and then you get an output y over here. Okay. So typically x is what is called as your input, w is your weight, b is your bias, you have a which is a pre-activation state, and then you have g which is an activation function, and then y which is whatever is called as the activated output or activation from a neuron. Okay. Now this total block, this summation and the nonlinearity taken together is what makes out a neuron. So here when g is something like a 0 or a 1, okay, so if the input to g is greater than 0, then you call that as 1. If the input to g is less than 0, then you call it then the output is 0. Now this is what is called as a perceptron model in this case, and that was first described by this person Rosenblatt in 1957. Okay, and in fact this was the first form of a neural network which was very easily defined. Now it's so easy to define. You can just do a 1010 kind of a classification, and then you can say, you don't even need to look into argmax or anything. You just say, okay, if this value is 1, then this is that class. If the value is 0, then it is not that class. This was that straightforward, hard cut rule over there. Now what happens over here is that you can have some others of them which are called as margin separations, and which is sort of like modified version of what Rosenblatt had done. So he says that if the value is less than 0, then let it be minus 1. If the value is more than 0, then let it be plus 1. And these kind of margin separation functions, nonlinearity, is essentially where by virtue of support vectors, which were getting very widely discussed around that point of time. Now if you look carefully into whatever this specifies, you can see that this essentially boils down to what is called as a hyperplane equation. Okay. See, this is just a matrix multiplication which took place over there. So W into X plus B. Now for any of our plane equation, if I had a 3-dimensional coordinate system, then my plane equation in a 3-dimensional coordinate system is Ax plus By plus Cz plus D is equal to 0. Now you can see that this is what is coming down over there. Now I can measure down the distance, and how this distance is measured is basically you write down something like D is equal to Ax plus By plus Cz, and then you know what are the values of A, B and C. You put down your values of X, Y and Z and you will get a value of D. Now if the point is on that plane, then this value of D is supposed to be 0. If the point is not on that plane, then the value of D is not going to be 0. It's going to be a non-zero number over there. Now the moment you get that, you essentially know that whether it's above the plane or below the plane. Now if the value of this whole thing is greater than 0, then you know that this is above the plane. If the value is lesser than 0, then it is below the plane. Then that is what happens. So essentially you can see that this whole thing will now start splitting everything in terms of some planes, and around that plane I can take a up or down or a left or right. Now you remember in the first class we were showing you something with separation margins and how to separate between data, and I said that the easiest of them was anyways a straight line. Now for a 2D case it was a straight line, for a 3D case it would be a plane, for a 4D case that becomes a hyperplane, but they are all linear equations which are present, not a linear system but a linear order equation which is present over there, and that's easier to do. Now comes this interesting part about the activation function. Okay. Now one activation function which you can have is that whatever is the input you pass that as the output, and this is going to be a pure linear. So essentially whatever is the rate of change of A will be the same as rate of change of G of A. Okay, good, you don't have to do any extra mathematics. Whatever comes as the result of this linear equation, I just give that as my output over there. From there we come into this another interesting thing which is called as a sigmoid activation function, and how that varies is somewhat that it is bounded like almost that perceptron models and Rosenblatt's activation function, that if the value of A is much larger, if it is tending towards infinity, then this becomes +1. If the value of A is tending towards minus infinity, then it becomes 0. Okay. If the value of A is 0, then it becomes 0.5. And then this is how it keeps on changing. In fact, you can add a coefficient over here, 1 plus alpha e to the power of minus A, then you would see that this slope will keep on changing as well. You can do something like 1 plus e to the power of minus alpha A, and you keep on changing the value of alpha, you will see this slope also keep on changing over there. And that has implications to our control plane of the problem. So this, more than what it has in the forward pass, it has a larger implication in the control plane, where you will have something which is on the reverse direction. However, on the forward pass also this has a very criticality. Why do you think we put these kind of functions, these kind of activations functions? One is to produce nonlinearity, and this kind of nonlinearity is what is called as a range nonlinearity. So earlier we had a domain nonlinearity. So in the domain of x's, things were not linear. But here you are going to have a range nonlinearity, which is if x is changing in a particular way, rate of change of x is not equal proportional to the rate of change of the output y over there. They will change at two different rates. Okay, this is one part of it. But beyond that, there is a larger implication. Why did we put something like a +1, -1? That will come a bit later. Okay. So till here, let's look into the forward pass. So I'm just putting in some inputs and I'm getting an output, and what will be an implication of this from a very systems understanding. Yes. Yes. So essentially there is something called as a system stability. So you would need that any system which you are designing, that system needs to be stable. And one of the criteria for system stability is that it needs to have a bounded input, bounded output behavior. So if my input is bounded, your output needs to be necessarily bounded. Plus on top of it, if I can somehow show that even if my input is not bounded, my output is still bounded, still I will be having a stability condition, because when I connect one system to the other system, if the first system can make my outputs bounded, that going as input to my second system is going to have an input bounded system. So subsequently, if all my systems are in a BIBO form, bounded input, bounded output form, then my whole system becomes stable. So I would need my neural network to be very much stable when it's just doing a forward pass operation. And that is why these nonlinear functions were given down over here. Now if not, what would have happened? See what happens with that saturation and how it relates to biology. Say that you are in a, how many of you have the tunnel escape experience? So you were driving into a tunnel and you came out of a tunnel and then everything became blinded. All of us have that experience. You enter a dark room and then you come out in a bright room and then everything is white for a period of time and then it takes you time to get adjusted to that whole part of it. Okay. Now that's because of this saturation. It's a temporary phenomena, but that was a saturation which was happening. Now why was that saturation happening? See, whenever we are sensing something, there is something called as a dynamic range. Dynamic range is the minimum value to the maximum value of whatever we are able to sense. Okay. Now there is also something which is called as resolution or contrast, at least for images or intensities. What that means is, in how many steps am I able to sense this lower value to higher value. So the number of steps in which we can sense, that is always constant for us. So as humans, we typically sense a minimum value to a maximum value in a step of 12. Nothing more than 12 we can sense. If we are sensing colors or something which is spectrally spread, then it boils down to even 6. This is what has been found through a lot of neurological experiments which are done with humans. Now that you have these levels which are fixed, the point is the only way you can change between your dark and bright is by changing the dynamic range over there, right? The whole purpose of doing this is such that your system is still able to resolve, but it does not get bloated out. So you have seen some sort of a connotation while taking images. So say you are taking an image in this classroom and you are also pointing your camera such that the scene outside the window is visible. Now the moment you try to get somebody in all the faces in the class, you adjust your brightness and everything such that all the faces are visible, you would see that the scene outside becomes totally washed off and white. If the scene outside is visible, then all the faces inside are blacked out. This is what is going to happen. So that's a problem with this whole dynamic range scaling which needs to go down. And here this also puts that kind of a constant over here. From a systems point, it has an implication as well as it has a one-on-one relation with biological neurons which we are looking at. There are other things which also vary between -1 and +1, and that was that margin kind of a loss which I said, and that can be achieved through a tan hyperbolic function. Okay. So similarly, you also have another function which is called as ReLU, or rectified linear unit. So what it does is, it's a funny function. So whenever the value is less than 0, it makes it 0. If the value is more than 0, then it gives the same value over there. So essentially what it says is that if you are positive, I will let you pass. If you are negative, I don't let you pass. So these are kind of systems which will make everything on your activation space become positive as well. So this is also one of those which does it. So you have everything in the range of 0 to 1 only. Here it says that it will have in the range of 0 to any higher value. Greater than 0 to any higher value. I am not restricted to essentially 1 over here. Whereas this one will restrict it to -1 and +1 necessarily. And then this one is whatever is my input and output, I will show it the same. There is no other way. Now, as of now, you can remember these activation functions from a BIBO perspective. When we come to the control plane of the problem, we will discuss further about what are implications which are produced by these and when you would like to have which kind of a function. Now, from a neural network, so essentially I said that this whole block in red is what is called as a neuron. So that typically we represent it something like this. So we merge this non-linearity over here into this whole part, and then we get our output, because essentially this AX does not have any big significance for us in any way. Okay. Now this will be our unit, which is also called as a neuron. This is a unity neuron which we have. Okay. So now let's go from having one single neuron to creating something which is called as a neural network. So we are looking at a very specific case which is called as a multi-layer neural network. So what it would mean is that there can be multiple such connections of neurons which can happen. Okay. So this is my input x1 to xd on this side. Now from my input, what I am having is I go and connect down to some number of neurons over here. So there can be some say a k number of neurons present in the first layer. Okay. Now this will take all inputs from x1 to xd. It will produce some k number of outputs. So over here I have 3, there are dots over here, so essentially there are. So say I have k number of ones in this first layer over here. So they will produce k number of outputs. Those k number of outputs can again be merged to another neuron over here. Okay. So essentially this input does not directly affect this one in a linear way. because there is a domain nonlinearity and there is a range nonlinearity which gets produced over here. Then on top of this one you have a range and a domain nonlinearity which gets produced over here. Now you can very clearly see that we are able to break down by order of model 1. The order of my model over here is still 1 because I just have hyperplanes. Okay. But then when I have one order 1 system with range and domain nonlinearity connected with another order 1 system, so essentially this together becomes a nonlinear system. Two successive order 1 polynomials multiplied with each other is going to give you order 2 polynomial over there. Now you can see how by way of this we will be able to increase our order of polynomial. So now getting back to our first class, so what we were telling is in a deep neural network what you are essentially trying to do is you are trying to simplify a bigger problem which has some higher order polynomial in order to come to that separation plane. You will be breaking it down into a set of multiple linear functions or order 1 functions and break it down, and this is essentially how that takes place. Now these intermediate ones from where we don't draw an output, so we don't draw physical output to look into it, is what is also called as a hidden layer. So you will have an input layer, you will have a set of hidden layers, and these intermediate hidden layers can be multiple as such, and you produce an output over here on the output layer. Okay, are we okay till here? So now from there if you look into the mathematics, so what happens typically is I go from one input, one neuron to one, so all the input points over here to one neuron in my hidden layer. The moment I go to this one neuron in my hidden layer, this is my set of linear equations which comes down over here. Okay, so I will have a set of weights which are associated, so which is sort of like a row vector which is associated with this first one. But then I have some k number of neurons in my hidden layer as well. So there will be a different set of row weights. My weights are in row, but there will be a different set of weights for each of them. It cannot be the same, otherwise it's going to produce the same output over there. Okay, so this becomes a row vector, and this you have this sort of like 1, 1, 1, 2, 1D, and this essentially means these different connections which are coming down over here. Okay, so this second subscript is what corresponds to the input from where I am connecting, and the first subscript connects to the output where it is connected. Okay, so this is like destination comma source is the nomenclature in those weights over there. Similarly, I go from this one to a different one. So in the second one I will have this kind of a form. So you would see that there is a superscript in a bracket of 1, which until we come to the actual training you will not be getting to that part. Okay, so this you can pretty much say that this is at the start of the problem. So at the initial condition I have this superscript of 1, and that is at my start of the problem. Okay. So this will become my set of linear equations for my second neuron in my hidden layer. Then I will have a set of equations for my last neuron in my hidden layer. Say that is M. Then this is my last neuron over there which will have my set of linear equations. Okay. Now from there I can essentially stack all of them and start writing in a very different way. So I have all of these weights which are basically rows. Each row is independent of each other. Okay. All my inputs in a column of X is the same to all of them. Okay. So now if I stack all of these weights over here, one below the other. So I do a column stacking of row weights, then essentially I am going to get a 2D matrix of weights. Okay. I will have this X which is still a column vector over here. Now as a result of this multiplication, what am I going to get? I multiply a rectangular matrix with a column matrix. So what do I get? What is the order of the matrix? Is it a one-dimensional matrix or two-dimensional matrix which I will get in the output? 1D. Okay. Will that be a row or will that be a column? That will be a column. So each column element is essentially what is representing this H over here for me after the nonlinear transformation. Okay. So now you see my whole neural network, which otherwise was looking so complicated, is just a multiplication of two matrices and nothing beyond it. Okay. Now here if we get into our output from there, so I obtained whatever was my input over here in terms of a column, and that column gets again multiplied by the same kind of a function over here through matrix multiplication, and then I get my output. And then I can have these activations over here which I can choose from anything between sigmoid, tan hyperbolic, ReLU or whatsoever. Okay. So now if you eventually keep on doing something, this is something which is called as a softmax activation function. So what it essentially does is that it exponentiates and then does it. So whatever is the output, e power of that value. Now one very important thing is that it can very easily, so it's limited between 0 and 1. because by virtue of that denominator. Along with that, it will push things like if something has a higher probability, then it will push it very closer to 1, and others it will push it very closer to 0. This is one of the important things which comes out as a result of this softmax kind of an activation function. So that's where we come to an end with this one on simple neural network building. So tomorrow we will get into some more connections. There are some connections which are called as recurrent connections. There are connections which are called as convolution connections. So tomorrow essentially we will start with convolution as an operation, and there are properties called as space invariance of convolution, which becomes very important when trying to deal with very physical systems and signals, more for images and signals itself. Thank you.